Well, hi guys. I think I promised you I was going to stop in and do a little bit more with this whole idea of elementary row operations and row echelon form of a matrix, and then show you how you can use that to then solve linear systems of equations. So this is a topic that is going to become routine for us once we practice it a few times, but it can feel a little bit tedious at first. So we need to practice it a little bit, I think, to kind of get the hang of it. You're always starting off with some kind of a matrix here, and the idea is to try to bring it into row echelon form by using those three elementary row operations, which are permutations of two rows, multiplying a row through by a constant, and finally adding a multiple of one row to another. So I'd like to practice that process of bringing a matrix into row echelon form. Let's take this matrix right here. Remember, row echelon form, any rows of all zeros have to go to the bottom, and the pivots, which is the first non-zero entry in each row, they have to go down and to the right as we look at the matrix. So looking at this one right here, the key idea is to figure out how am I going to get a 1 in the upper left corner. That's kind of the first step. And there's more than one way to do that here. You could add the third row to the first row, because the -3, when you add it to 4, would make a 1. In this case, though, there's another way that we could do it. And either way is fine, but I'm just going to choose to do it this way. I'm going to multiply the first row by 1/4. A lot of times when you multiply through by a fraction, you create a lot of fractions in this matrix. But what I notice here is that all of the entries on the top row are multiples of 4. So when I multiply through by 1/4, I actually have not created any fractions at all. So I'm multiplying row 1 by 1/4. Okay, so here is what we would have after that step. Once you have your pivot where you want it in the matrix, the upper left corner, the next step is to get everything below that pivot to become a 0. And that's because we need the pivots in these lower rows to be further to the right than the first column. So I'm going to do everything I can to make zeros out of these two entries right here. Now I'm not going to be able to accomplish that unless I use the A operation. I'm going to add multiples of the first row to the lower rows. So let's do this. Let's take A12 of -2. So I'll remind you that what that means is that you're going to take the first row times -2 and add it to the second row. The first row actually isn't going to change at all. In fact, for the whole rest of this problem, the first row is not going to change. Okay? But now, on the second row, when I multiply the top row by -2 and add those results to the lower rows, this is what I should now have for the second row. Okay? So -2 times each of the 5 numbers in the first row is being added to each of the 5 numbers in the second row. All right. At the same time, I also want to get a 0 right here in the 3-1 position, and I can accomplish that with A13 of 3. I don't mind if you do these at the same time. Those two adding operations do not interact with each other, so there's really no confusion about them, and I can just notice the relationship from the 1 to the -3. If I take 3 times the first one, I'll get something I can add to -3 and end up with 0. Okay? So I'm going to take 3 times everything I see on the top row, and I'm now going to add that to the last row. Okay? So I'll get 0, -10, 1, -7, and 2. Something like that. Okay? And now I actually have already got a pivot in the second row. So this is fantastic. This is exactly what we wanted, was to get the pivot in the second row to the right of the pivot in the first row. Okay. My next job is to get everything below this pivot equal to 0. So I'm going to do a 2, 3 of 10. I'm going to take 10 times the second row and add it to the third row. That's going to keep the second row the same. Second row doesn't change. And if I take 10 times the second row and add it to the third row, well, I'm going to get some fairly big numbers here in the last row of the matrix. So that's 10 times the second row added to the third row. I like to put diamonds around my pivots. You're probably noticing that already. This is a very good practice. That keeps you informed about where your pivots are and what you're trying to accomplish. Okay? The only thing left to do now is to make this 31 into a 1. And this is going to involve introducing a pretty nasty looking fraction. But at the same time, we're also almost done. So if we're almost done, it doesn't really hurt us very much if we just go ahead and multiply through by 1 over 31. So we're going to get some fractions here at the end. But like I said, we now have our pivot structure exactly according to the rules of a row echelon form. So this would be an answer. Not the only answer, but it is one good answer for the row echelon form of this matrix. Okay, I want to make a note, kind of alongside this, along with the definition. The number of pivots that you get in your row echelon form has to agree with the number of pivots that anybody else would have gotten by finding a row echelon form. In other words, it doesn't matter what elementary row operations you've chosen to do here. The one thing that is common to all correct answers for the row echelon form is the number of pivots. Okay? So let me just point that out. All row echelon forms of A will have the same number of pivots. Okay, so if this matrix here is the matrix A, right, then the number of pivots is 3 for this matrix, right? It's not always going to be the number of rows of your matrix, because remember, you could get a row of all zeros in certain situations. But whatever that number of pivots is, this is called the rank of A. This is a very important concept, the rank of a matrix. It's the number of pivots in the row echelon form of A. And everybody has to agree about what the rank of a matrix is, no matter which elementary row operations you might have chosen to do. Okay? So this is an example of a matrix that has rank 3. We could have done this problem with different row operations and maybe would have had a different answer down here. But 3 would have been the number of pivots. Okay? I'm going to erase this. You can certainly pause it, double check all of my work. You have to be very careful because it's easy to make minus sign errors or just writing one number in the matrix down incorrectly at one step. The errors tend to mushroom. From there, it's very hard to get back on track. So when you're doing these problems, guys, try to be really careful. Stay focused so that you don't make any arithmetic errors that would lead you to, well, the wrong answer and perhaps some very messy calculations. Okay, what I want to show you in the second half of this video is I just want to explain how you use this method that we just discussed to actually solve linear systems. And that's what Gaussian elimination is. So this is in section 2.5. Gaussian elimination is really the process of using elementary row operations, row echelon forms, and so on to solve a linear system. So let me give you an actual example. This is going to be the easiest way to show you. Let's suppose I want to solve the following linear system. 2u minus 3v plus w minus x plus y equals 0. And then the next equation, 4u, okay, minus 6v plus 3w, I'm sorry, plus 2w minus 3x minus y equals 0. Okay? And then finally, negative 2u plus 3v minus 2w plus 2x minus y is equal to, oh, I'm writing this wrong. This should have been a negative 5, and this one should be a 3. Sorry. That's what the system is supposed to be. I just didn't copy it down that efficiently. So this is our linear system, and we would like to solve for the unknowns. So the goal here is to figure out what is u, v, w, x, and y. If possible. Right? Some linear systems have no solutions. If there's no solution, then, well, we won't be able to solve for the variables, right? But hopefully we can solve for u, v, w, x, and y. The first step to this is going to be to just put this linear system into an augmented matrix. I'll call it A sharp. Okay, so we've done this before. You simply have to write down the coefficients of the system. We're going to augment this matrix with the right-hand side vector as well. So this is just recopying all of the numbers from the system into a matrix. Okay? As we're doing that, I don't want you guys to forget that there are really variables attached to each and every one of these columns. U, V, W, X, and Y, right? The coefficients in front of U are the first column of this matrix, right? And so on and so forth. Okay? What we're going to do now, guys, is we're going to use elementary row operations to bring this matrix into row echelon form. Okay? So, now you could take the first row and multiply it by 1/2, but that's going to create fractions right off the bat. What I think I'm going to do instead is I'm going to leave the first row the same. I'm not going to touch it yet. So we'll leave the first row the same. I'm going to use this 2 to zero out the numbers below it. Okay? So I'm going to do the following. I'm going to do A12 of -2. So I'm going to take -2 times the first row and add it to the second row. You see why I'm doing that? There's a 2 here and a 4 here. I want this 4 to become a 0. So I'm taking -2 times the first row, and I'm going to add it to the second row, and I'm going to get a 0 right there. And I now have to go all the way across the matrix with that same multiplier. -2 times -3 is 6. I add that to -6, I get 0. Right? -2 times 1, I add that to 2, I also get 0. -2 times -1, that's 2. I add that to -3, I get -1. -2 times 1 is -2. I add that to -1 and it becomes -3. And the -5 is going to stay the same. Okay? Similarly, I'm going to take A13 of just 1. In other words, I'm going to add the first row times 1 to the third row. So the first row added to the third row, I'm going to get 0, 0, -1, 1, 0, and 3. Okay? Excellent. Now, I have several other things I need to do. I know that eventually this will become a pivot right here. It would be even okay to sort of circle your sort of leading positions right now. You can see it's not in the proper form for the row echelon form. But what I can do is I can permute rows 2 and 3. See, the pivots need to go down and to the right, so I'm going to switch the second and third row. So if I do that, of course I'm not doing anything to the first row yet. I'm going to put the last row second. Whoops. I'm going to put the last row second, and I'm going to put the second row last. Okay, so just permute the second and third rows. Now my pivot structure looks good, And I just need to multiply by the appropriate scalars to make all of those pivots equal to 1. So what I'm going to do here, I'm going to multiply the first row by 1/2, and multiply the second row by -1, and multiply the third row by -1. It's perfectly safe to do all of those at the same time. You notice that when you're doing the same type of operation of either adding or multiplying, it's a pretty safe thing to just do them in kind of in one step. Okay, so I am going to get some fractions on this first row when I multiply by 1/2. Okay, the second row I'm just doing a sign change really. And the third row I'm also just doing a sign change. Okay? Now we should stop and ask ourselves, what is the rank of this matrix here? This is the rank of A sharp. Remember, it's just the number of pivots in the row echelon form, and there are 3 of those here. So this is a matrix of rank 3. All right, and we've got it into a good row echelon form. Now, once we've done that, the question is, how do we now go back and get the solution to our system? Let's remember that there are variables associated with these columns, u, v, w, x, and y, right? We're going to need to keep track of that. We can actually go back if we want and write down the 3 equations that this matrix is giving us. So we started with a bunch of equations and we made a matrix out of them. You can also take a matrix and go back and write down equations out of those. So for example, the first row of your matrix that we have over here, the row echelon form, the first row would be exactly this equation right here. The coefficients of u, v, w, x, and y are just the numbers on the first row. Okay, and then we have w minus x equals -3, and then we have what? X plus 3y equals 5. The pivoted variables, the u, the w, and the x, right? U, w, and x, these are actually referred to normally as leading variables. They are leading the equation. They are the first variables in the equation that you're looking at there. The other variables, let's see, that would be v and y, that are not leading, they do not have pivots associated with them, those are called free variables. So we have leading variables and we have free variables. And every variable is one or the other, right? Every variable has to be one or the other. Okay, so this is the set of equations that we have. So we've gone back to the system of equations. The original linear system is here. And remember, guys, that no solutions have been gained or lost through the elementary row operations that gave us this system. The matrix that the work I was doing over here, that was just the vehicle that took me from the original linear system to this linear system. This one's as good as it's going to get. Okay? It's as good as it's going to get. We're not going to be able to do any other EROs to get ourselves in any better position to be able to write down the solution. Remember, we're trying to solve for the unknowns here. How do we do it? Well, what we do, guys, is we recognize that y, I'm going to start from the right to the left. Remember back substitution? You start on the bottom of equations and work your way back up. But the very first variable that I see on the last equation here, if I look at the right side of it, is that the y is a free variable. I like to change my letters. I usually like to use R, S, and T for free variables. It just reminds me that that's what I'm doing, right? I'm assigning a free value to y. What it's saying is that y can be any number that we want, right? Y can be any number that we want. Now, x cannot be any number that we want. X has to be 5 minus 3y in order for this last equation to be true. In other words, x is going to be, what is it going to be? It's going to be 5 minus 3t. I'm going to try to write all of my 5 variables, u, v, w, x, and y, in terms of my free variables which are going to be things like r, s, or t. Okay? Great, so we started off by establishing y as a free variable. We've now written x in terms of that same free variable. I can do the same thing with w. If I come now to the second equation in my list here, if I solve for w, w is just x minus 3. Right? The middle equation just tells me that w is just x minus 3. So just in the same way that we used the last equation to solve for x, I'm using the middle equation to solve for w. If I take x and I subtract 3 from it, well, that's going to give me 2 minus t. Is it 2 minus 3t? 2 minus 3t. So that's w. Okay? Now I go back to the top equation. I've already established y as a free variable. I've solved for x in terms of that free variable and w in terms of that free variable. The next variable that I see is v. And we have not seen v so far, so I'm going to establish a second free variable. Let me call this one r. Okay, I like to use r, s, and t typically. So we'll use r for this free variable. And if I do that, then I can actually solve for u. Notice we are going to have expressions for u, v, w, x, and y here. Okay? So what is u going to be? Well, it's 3/2. So I have to actually take this first equation and I have to move everything to the other side of the equal sign. So it's 3/2 of v, which is r, and then minus 1/2 of w, but w is 2 minus 3t, right? And then plus 1/2 of x, but x is 5 minus 3t, and then plus 1/2 of y, which was just t. Okay? So what I'm doing here is I'm expressing u totally in terms of r and t, my free variables. Okay? Remember, the free variables can be any numbers that we want. We can choose t and r to be our favorite two real numbers. And once we know those numbers, we will be forced to calculate x, w, and u from this set of equations that we're writing down here. Now this one can be simplified just a tiny little bit here. Obviously the 3/2 r is kind of standing alone. But we have, what do we have here? We have about 3/2 of t, and then minus 3/2 of t, and then plus 1/2 of t. So when you simplify that, you would just get 1/2 of t. And then here we have a minus 1, and then a plus 5/2, so that would be plus 3/2. So that would be the values of our variables. Okay, and let me just make sure that that looks okay to me. So we have 3/2 of r, and then, yeah, I think that looks okay. I've got something slightly different in my notes here. I've got 3/2 of r minus 1/2 t, and here I wrote plus 1/2 t. Is that right? So we have a half of a t there. It looks like, yeah, minus. Yeah, I think that looks right. Okay, so anyway, it's not what my notes have, but I'm going to take it as the right answer for now. So we have u, v, w, x, and y, and so then we can write down our solution. Okay, I'm going to write down the solution to the system, and there are actually infinitely many solutions to this system. Okay, we're going to get out these big braces that I think I showed you guys in class last time. And we're going to list the variables. Make sure you do it in order. U, then v, then w, then x, and then y. So u would be 3/2 of r plus 1/2 of t plus 3/2, comma, and then the v would just be r, comma, w is 2 minus 3t, comma, x is 5 minus 3t, comma, and then y is just t. So we've made a 5-tuple here, right? 5 numbers representing u, v, w, x, and y in that order, right? So this is u, this is v, this is w, this is x, and this is y. Then I'm going to use a little bit of math notation here. This little colon just means such that, okay? So it's that set of 5 tuples such that r and t belongs to So this is a little sort of lowercase e means belongs to. And then here we have the real numbers. This boldface R is the real numbers. Okay, and then we end our braces like that. So this would be your answer. Okay? There's infinitely many solutions to this system. Okay? Well, I hope that makes sense. I'm almost done. I just want to show you what would happen if the system didn't have any solutions, right? What if we had something like, x plus y equals 2 and x plus y equals 3, right? We can look at that and we already know there's no solutions to this system, right? Well, when you go and put it into your augmented matrix, this is how it would look, right? It's a very easy one to do. And we could just do a1, 2 of -1 on that. So in other words, we would just take the negative of the first row and add it to the second row. And this is what we would end up with. A pivot in the far right column. A pivot in the far right column. And that means when that happens, your system is inconsistent. Because look, what are you really saying here on the last line? 0 times x plus 0 times y equals 1. And that, of course, is ridiculous, right? You cannot solve that for x and y. So the Gaussian elimination will lead you to an inconsistency in the cases where that's what it's supposed to, by giving you a pivot in the far right column. So if you see a pivot drifting into the far right column, that means it's going to be inconsistent. Okay? So there really are, just to kind of summarize here, there are 3 possible outcomes to Gaussian elimination. 3 outcomes to this process. And every single problem that you get asked to do, solving a linear system, is going to have one of these 3 outcomes. First of all, the system could be inconsistent, which just means 0 solutions. And that happens if you get a pivot in the far right column. So in other words, past the augmentation bar here. If you get a pivot to the right of that, your system has no solution. Okay? A second possibility is, let's suppose that doesn't happen. Your system might be consistent, but maybe this is with no free variables. So you have no variables that you can put a t with, that you can assign t to. In other words, when you solve by back substitution, you get specific numerical values for each and every one of your variables. So your matrix is going to look something like this. You're going to have a pivot, a pivot, a pivot, a pivot, let's say, and then there's your augmentation bar right there, right? The rest of the numbers, I don't know what they are, right? But the point is, there's no unpivoted columns, right? Why was the v and the y? Why were those free variables? It's because they were not leading variables. They had no pivots on them. Okay. But if every variable has a pivot like this, then when you solve by back substitution, you will just get one solution, right, that has specific numbers in it. And finally, you could be looking at a system that is consistent with free variables. And that's the situation of what we had over here. The minute you have free variables, of course, you have lots of solutions because you get to choose those variables freely. You get infinitely many solutions. So every linear system has either no solutions, one solution,